Welcome back. This is week 9 of inverse methods in heat transfer. In this video, I'll be talking about some variations of gradient descent. These are called batch gradient descent, mini batch gradient descent, and stochastic gradient descent. Now, all these are particularly relevant for two reasons. So, if you recall gradient descent, so if you remember what gradient descent was, it was a simple idea that when you have a parameter W or a set of parameters W, you basically update them as W minus alpha times del J del W. Okay. So if you have two parameters in particular, you would have something like this, and W1 equal to W1 minus alpha del J del W1. We saw this earlier in the course. So for example, let us say J was equal to 1 over the number of examples, y minus y hat square, I equal to 1 to m. So for example, our slab case, suppose I am solving for these parameters W0 and W1, and y hat is W0 plus W1x. Then all I need to do is to minimize J. And for minimizing J, I basically use these expressions. So we would first guess. So the general algorithm for gradient descent was we would guess for W0, W1, etc. and then update. But all this, of course, requires this expression, the gradient expressions. So we are going to call these the gradients, which is why we call this the gradient descent. Now, our key task here is to evaluate this del J del W naught. And as you will see both this week and next week, this is a very important ingredient of any optimization algorithm. But what was del J del W naught? Again, you might remember from our earlier classes that del J del W naught was calculated as del J del Y hat multiplied by del Y hat del W naught, which came to 1 over m sigma I equal to 1 to m. I would request you to check out your earlier notes yi minus y hat I. Okay. Similarly, del J del W1 turned out to be del J del Y hat times del Y hat del W1, which was 1 over m sigma of I equal to 1 to m. In fact, we had calculated these several times, y hat I minus y hat I times xi. There was a negative sign also in front. Now notice this, notice these terms. Okay. There is a special feature in these terms. Both involve summing over the entire data set. Okay. So notice this entire data set, the sigma that we have is over the entire data set. Again, in earlier programs, or in case you used an Excel sheet, this would have become clearer. What we would have done, remember, each one of these terms is the error. So what this term says is W naught is updated by the difference between yi minus y hat I and the average error over the various examples that you take. So once again, let's go back to our model. In case we are fitting a temperature model and the actual temperature is something else, we see the difference between what we are predicting, the model, versus what reality is. That's what is written here, y hat I minus yi, and sum and take an average. Okay, but what this requires is summing over the entire data set. For what? For each update. What does that mean? So remember, I had given you a short example of gradient descent earlier also. Suppose you start in W0, W1 axis, and you're starting with some initial guess. Let's say this is the guess 1, 1, and you move to a different point and say this is the optimal point, which is 1.1, comma, let's say 0.8. This is one update. One update means W0 has been updated. You have made a new guess for W0, and W1 has been updated and you have made a new guess for W1. But for one update, we require to sum up over the full data set. Okay. Now, this is fine when we are doing the sort of examples that we did in class with 5 or 6 thermocouples. But as we will see in 2 weeks from now, or even a little bit in the next week, though I will not be showing any major examples, in real machine learning, okay, usually data set has 2 problems. First, it is huge. So in some of the image data sets, you could have millions of images. So in case you make a prediction, you would actually have to do the summation over a million images before you make one small update. Now, we also saw earlier on that with iterative methods, you might not converge in just one update. You might require like millions of updates. So this becomes really expensive. Okay. Second, data set could be dynamic. That is, so let us say you are in an industrial setup and you have instruments constantly making measurements. Now, if you use the normal equation approach, has this problem. Remember our X transpose X delta W, or in our case, I wrote W equal to X transpose Y. Now, this requires matrix setup. And the moment I give a new X, you can't update it. You have to solve the entire problem again. But even in gradient descent, you have to do this entire sum again because the summation is from I equal to 1 to M. So in both these cases, it's somewhat disadvantageous to use gradient descent, though gradient descent works kind of okay with dynamic data sets, but it doesn't necessarily work well with huge data sets. So we have a couple of other variants, and these are very natural variants of what we do. So what we have done is this version of gradient descent, the vanilla version or the normal version of gradient descent, is called batch gradient descent. Batch gradient descent means that one update requires full data set. Okay. Another way to say it is, this is called one epoch. One epoch means the update or the gradient has seen full data set. Now let's go to the other extreme. The other extreme is what is known as stochastic gradient descent, SGDE for short. Now, how does this work? So let's take our data set, the usual X, Y, Y hat. Let's say we have X1, Y1, Y hat 1, up till, let's say, X100, Y100, and Y hat 100, Y hat 100. Okay. So now, when we do W0 equal to W0 minus del J del W0, we take only one data point for this calculation. That is, del J del W naught is simply calculated as y1 minus y hat 1. Okay, so notice here, this was y1 minus y hat 1, sorry, negative of that. Always keep on making this mistake. Minus y1 minus y hat 1. Remember, you have to sum up over a certain set of data points and then do 1 by m. And I am basically setting this m equal to 1. Okay. So, and then I'll do w naught equal to w naught minus del j del w naught. Okay. Similarly, w1 will be w1 minus del j del w1, where del j del w1 is only calculated for the single data point, y1 minus y hat 1 into x1. Okay. Now, how does that help us? Now, once I do this, I get one update. So instead of getting stuck at this point, I actually move a little bit. Maybe I'll move in a different direction because this is an average of the entire data set. This is just what one data point predicts. But I am moving. Okay, so I am making shorter steps, but I am at least moving more rapidly. By the time I see all data points, I would have perhaps moved further down. So what I do is this. The second step will be W naught equal to W naught minus del j del w naught, where this del w naught will be now calculated for the second data point. So one more update. Okay. So this will be minus y2 minus y hat 2. So on and so forth. So we can write the algorithm this way. The algorithm for stochastic gradient descent first is initialize or take a guess for W0 and W1, or how many other parameters we have. We will call this the 0th iteration. And then we will say W0 for the k plus 1th iteration is W0 at the kth iteration minus del j del W0. Okay. Now this one is calculated sum over all data points. So similarly for W1. Okay. And then you repeat this. So what does that mean? It means that I update W0 once here, W1 once here. Once again, I update it here. And by the time I see the entire data set, so remember I call that an epoch. Hundred updates. Okay. So gradient descent updates for each data point separately. Okay. So when you do that, typically we notice that you will go a little bit like this to the final point. Whereas batch gradient descent could have gone a little bit more smoothly. So this could be batch, this could be SGD. But SGD is typically faster, but less stable. Okay, it might go. This is just like a very active person. They tend to get things fast, but they'll make a little bit more mistakes. So SGD is faster, but it's a little less stable than batch gradient descent. The advantage also with SGD is it's good for large and or dynamic data sets. I'll show you a demonstration of SGD versus batch gradient descent in the next week when we come to a full treatment of neural networks. Now, there was a third thing, which is kind of an obvious measurement or on a modification of the two, which is called mini batch gradient descent. Now, mini batch gradient descent works like this. Suppose this is our block, again of X, our data set X, Y, Y hat. Now, instead of, let's say, again, we have 100 points. Now, instead of taking either completely 100 or a completely 1, we can go somewhere in the middle. Let's say we take mini batch size of let's say 10, or let me call it 5. Okay. So I take 20 sections. Okay. So this is mini batch 1, mini batch 2. Again, I take 5 data points 6 to 10, 11 to 15, so on and so forth, till mini batch 20. So what do we do in this expression? Which is W equal to W minus del J del W, whether it is W0 or W1, it doesn't matter. The del J del W is calculated, let's say this is W1, is calculated as 1 by B sigma I equal to 1 to B of yi minus, or y hat I minus yi into, let's say, x1 of the ith data point. So what we will do is, first we will take an average over the first 5 points, next over the next 5 points, third time over the third 5 points. So basically, in one epoch, we will have 20 updates. So in general, if the data size is, or data set size is M and mini batch size is B, then we will have M by B in one epoch. Of course, you want to, what is the significance of one epoch? One epoch is when you have seen the entire data set. That is, for example, you have 100 thermocouple measurements. You have made sure that your parameters have seen all these 100 measurements, and then only you're happy. Okay, but nonetheless, and that's also what is an apples to apples comparison. Because if I compare batch gradient descent for each update, it is looking at all 100 points and summing up over it. If I look at stochastic gradient descent, it's only looking at, it has a very quick calculation, one data point. If you do it by hand, you will see you just have to find out one prediction that you made versus one prediction which is of the ground truth. But by the time I do 100 of those calculations, I might actually move further than the batch gradient descent has. Like I said, you can think of these three people as some extremes. Batch gradient descent is a very careful person who does not want to make a move, or doesn't want to say where I should go next before I have looked at all the data. Stochastic gradient descent is like a very judgmental person. It's like one point of data, it will move immediately. Whereas mini batch is somewhere in the middle. It's like, okay, I am not satisfied with just knowing one thing. I'll see at least a few points, then I'll make a move, and then I'll see the next data point, and then I'll make a move. So this person looks at partial amount of data, but is at least a little bit action oriented. SGD is fully action oriented. Batch is like fully thought oriented. So this kind of difference is often shown between batch gradient descent, mini batch gradient descent, and stochastic gradient descent. While reaching the optimum, let's say the red point is the optimum you want to reach. Batch gradient descent will reach there, but it will take a lot of computation, but it will reach smoothly. Stochastic will go all over the place, and mini batch is somewhere in the middle. Often we either use in practice, like I said, if you have data sets which are coming very, very rarely or very dynamically, something like mini batch or stochastic gradient descent makes sense. If you have a small data set, you want some smoothness. So batch gradient descent makes sense there. So now what we will see starting from the next video is how these ideas, gradient descent, etc., can be applied to the idea of classification. Specifically, we'll look at two algorithms, the logistic regression algorithm and the multi-class classification algorithm. So I'll see you in the next video. Thank you.